Hello everyone, welcome back. So, today we are going to discuss two classic problems. Firstly, the first one is dining philosophers and sleeping barber. So, if you want to learn about those two problems, stick aside. Now, imagine you are at a dinner party with friends, but there's only one bowl of spaghetti for everyone. Chaos, right? Or picture a barber shop where the barber falls asleep mid haircut. These aren't just funny scenarios, they are a real world puzzle in computer science. Today we are solving the dining philosophers and sleeping barber problem. Now, firstly, computers juggle thousands of tasks at once, like handling your Netflix stream while downloading files. But how do they manage all these tasks without crashing? That's where concurrency control comes in. Two famous problems that teach us how to share resources are dining philosophers. In this, five philosophers think computer process sharing works, that is resource at a table. Then the other is sleeping barber, a barber resource who dozes off until customers process arrive. These problems aren't just in theory, they are the reason your apps do not freeze or crash. So, firstly, the dining philosopher's problem. Now imagine there is a circular table with philosophers and folks. So picture five philosophers at a round table. Each one has a plate of spaghetti, but there are only five folks, one between every two plates. To eat to eat a philosopher we need two forks, obviously, left and right. The catch: if everyone grabs a fork at the same time, deadlock. What is deadlock? If all the process are trying to access the resource at the same time, that is a deadlock. Everyone's stuck holding one fork, starving forever. X. So how do we can fix this? Firstly, we will just a second. So, what is the solution? First one is resource hierarchy. We will assign numbers to the folks. Always pick the lower number folk first. No more circular waiting. Then the arbitrator. Add a waiter. Philosopher will ask permission before grabbing the folk. Only one philosopher eats at a time and the four waits. Then we can also have timeout. If a philosopher cannot get both the folks, they put them down and try later, just like us waiting for a bathroom. Yeah, yeah. This isn't just about folks, it's how computers manage printer, memory, or your Wi Fi router without any rules. Everything grinding to a halt. But why dining philosopher matters in a computer system? So, firstly, it represents the resource allocation problem in computing, which is very complex. So, the dining philosopher, by studying the dining philosopher problem, we can solve deadlocks. Deadlock means that no process can proceed. The real world example will be managing the database lock, network traffic control, or allocating CPU resources efficiently so that we can utilize the maximum CPU output. Now, after this, let us go to sleeping barber. So, what is sleeping barber problem? Now, a barber shop. Let us visit a barber shop. There is one barber, a few waiting chairs, and customers who come randomly. So here is the problem. If the shop is empty, the barber sleeps. Okay, right. If the shop is empty, the barber sleeps. A customer either wakes the barber, waits in the chair, or leaves if all the chairs are full. So how do we coordinate this problem? Both the problem, if the barber gets sleep or the customer leaves or wakes. So we can think of semaphores with the help of semaphores. Let us think of them as a traffic light. A barber semaphore 0. Initially, the barber is asleep. A mutex to protect the waiting chairs counter. Then a customer semaphore. Why customer for? Just a second. So why a customer semaphore? Because to signal the customer. So this is how it will work. The customer arrives. It will check chairs. If full, leaves. If the chair is free, they sit, increment the waiting count, and signal the barber. Barber wakes up, cuts hair, then checks for more customers. If none, sleeps again. So, how if no customers, the barber sleeps? Okay, right? Okay, now why did all these problems matter? Firstly, in the barber problem, it is like a coffee shop with one barista. You either get coffee immediately, wait in line, or wait if the line is too big. Semaphores are like the baristas. Next place system. Yeah. So why these problems matter? Whether the dining philosopher problem or the barber problem. So these problems teach us three golden rules of concurrency. That is, avoid deadlocks. It means that no process should starve for resources. And also ensure fairness. It means that everyone gets a term with the same amount of time. Then we have to optimize for resources also, because we do not want to waste a CPU time or memory. From from self-driving cars to Netflix servers, these principles keep running smoothly. Imagine if traffic lights did not sync, the whole world will stop. Now let us see all the problems in real world scenarios. Firstly, the dining philosopher problem. Have you ever tried booking concert tickets online? The system will use similar rules to stop 10,000 people from grabbing the same seat. Then, it's a sleeping barber. If you have used Uber or any food delivery app like Zomato, the drivers or the barbers sleep until request or customer arrives. The app manages the waiting chairs to avoid overload. Now, let us recall what we have learned so far. Firstly, we have learned about dining philosopher. It means that we have to share the resources wisely and avoid deadlocks with rules or a waiter. Then the sleeping barber. We can should use semaphores to coordinate limited resources and waiting lines. So next time your phone multitask smoothly, remember it is using these very principle. So if you enjoyed this, smash that like button, subscribe, and tell me in the comments what is a real life concurrency problem you have faced. Laggy video call, online shopping crashes. Let's geek out together. Until next time, keep thinking, keep learning. Thank you.